Here are the sample problems for Math 117, Class 19. I'm not going to do the proof in these sample problems because it's the subject of the second batch of workshop problems. Okay, here's our first little result. X sub t is a martingale. It's a random variable indexed by a continuous parameter, the time t, and as you know, if such a martingale is bounded, it converges to a limit, which we'll call x infinity. Here's what I'm going to prove. I'm going to prove that if I pick any random variable that is f sub t measurable for all t greater than s, then the product of that with x infinity conditioned on the sigma field at s is exactly the same as the expectation of y times x sub t conditioned on f sub s as long as t is greater than or equal to s. And here's why I can prove this. The sigma field at t is generated by a finer partition than the sigma field at s, because at t, the later time, you have a variety of futures for every event at s. Every event at s is the union of paths that extend on into the future in various ways. So I'm going to use the Tower law backwards. Here's how. Instead of just conditioning on f sub s, I'm going first to condition on x sub t to get a new random variable. And then I'm going to take that random variable and condition on an f sub s. And since f sub t is a finer partition than f sub s, this isn't going to make any difference. Okay? What can I do now? Well, I know that y is f sub t measurable, and therefore I can take it out of the conditional expectation, leaving just f sub t there. I have simply taken out what is known. And then I look at x infinity conditioned on f sub t, and I say, because x sub t is a martingale, the expectation of x in the future conditioned on f sub t is just equal to the value at t. So this is just y times x sub t conditioned on f sub s by virtue of the Martingale property. Okay, the second part of this problem is a specific example. I'm playing roulette in a fair casino where the where there's no 0 on the roulette wheel. So if I say bet on red, I've got a 50% probability of winning, a 50% probability of losing. I start out at n equals 0 with 1 chip. And after my first play, having made 1 play, I have 2 chips with probability 1/2, and I'm broke with probability 1/2. If I'm broke, I just stay broke. So after 2 plays, I have 0 chips, again with probability 1/2. But if I have 2 chips at time 1, I keep playing, and with a total probability of 1/4, I'm up to 3 chips. With a probability of 1/4, I'm down to a single chip again. If I have a single chip, I bet it, and with probability 1/8, I'm back up to 2 chips. If I have 3 chips, I declare myself a winner and stay there. And now the probability that I'm flat broke is 5/8. Notice those probabilities sum to 1. And furthermore, my expectation is 3/4 plus 2 times 1/8, which is equal to 1, just what I started out with. Finally, to finish off the beginning of this process, I bet a chip if I have 2 of them, and I have 1 chance in 2 of winning on that bet, which brings my probability for having 3 chips up to 5/16. There's a 1/16 probability that I'm down to 1 chip, and I've still got a probability of 5/8 of going broke. What's going to happen after a very long time? Well, this is a martingale, so my expectation has to remain 1 at every stage. After I played for a very long time, I'll either have 3 chips or 0 chips, and therefore there's a probability of 1/3 of having 3 chips, a probability of 2/3 of having no chips, because that's what makes the expectation 1. Okay, now let's pick a random variable y. I'm going to make a rather simple choice. I'm going to choose the indicator function of the event I have 2 chips after 1 play. So y equals 1 on paths through this circled node. And the little result I just proved says that if I take the expectation of that random variable y, or any other random variable, times x sub t for any t greater than or equal to 1, and condition on the situation at 1, I'm going to get the same result for all time. Well, let's consider the expectation of x infinity times y conditioned on f sub 1. I've chosen s equals 1. If I have 2 chips at s equals 1, this is a martingale, and therefore the value at any time in the future is going to be 2 if x1 equals 2, 0 if x1 equals 0. What about intermediate times? Well, let's look at x2 times y conditioned on f1. If x1 equals 2, that's 1/2 times 3 plus 1/2 times 1 equals 2 if x1 equals 2 and 0 otherwise. Similarly, if I look at x3 times y, y is taking all these paths and multiplying them by 1. So at 3, I have a 50% probability, having been through this node, of still being there. And I have a probability of 1/4. The probability here is 1/8, but conditioned on my having 1 on the first trip, it's a probability of 1/4 to follow that event. And that's equal to 2 and 0 otherwise. And finally, if I look at x4 times y conditioned on f1, I have 5/8 times 3. That is conditioned on my having won my first play at the roulette wheel. I have a 5/8 probability of ending up with 3 and a 1/8 probability of ending up with 1, and that's equal to 2, which confirms in this very simple case the result I proved earlier. The next problem is the one preliminary result for the proof that I haven't asked you to prove in the workshop. I'm going to prove it myself. I'm going to prove that the expectation of e to the capital X, where x is a random variable, in the special case where the random variable x is normally distributed with 0 expectation and variance sigma squared, this expectation is simply e to the 1/2 sigma squared. How do we prove it? Well, we start by writing down the density function for the normal distribution. And the density function is 1 over the square root of 2 pi. Because the variance is sigma squared, I have to put the sigma squared under the square root sign and write e squared equal to e to the minus x squared over 2 sigma squared. And using that density function, I can calculate the expectation of any function of the random variable. All I do is integrate the density function from minus infinity to infinity times the function in question, which is e to the x. Now, I've got to fiddle around a bit with this exponent. We've got an x squared over 2 sigma squared, and with the opposite sign, we've got an x. Let's put that over a common denominator of 1 over 2 sigma squared times x squared minus 2 sigma squared x. And now comes the trick. I need to complete the square. So I write this as x minus sigma squared quantity squared. That gives me x squared, and it gives me minus 2 sigma squared x. Unfortunately, it also gives me an extra 4 sigma to the 4th, so I have to subtract off 4 sigma to the 4th in order to make that correct. Or I have ended up with x minus sigma squared quantity squared over 2 sigma squared minus 2 sigma squared. So now let's go back to our original calculation. This expectation is, this all came out with a sorry, I messed up my algebra a bit there. There's no 4 there. I've got an extra sigma to the 4th that I have to subtract off. So this extra term is minus sigma squared over 2, which is what I want. Now this was the negative of the exponent, so I've got e to the sigma squared over 2. That goes outside the integral sign. And then I've got 1 over the square root of 2 pi sigma squared times the integral from minus infinity to infinity of e to the negative x minus sigma squared quantity squared over 2 sigma squared with respect to x. How am I going to deal with that? I set y equal to x minus sigma squared, so dy is just equal to dx, and I've got e to the sigma squared over 2 times 1 over root 2 pi sigma squared times the integral from minus infinity to infinity of e to the minus y squared over 2 with respect to y. And because the density function for the standard normal distribution is properly normalized, this is equal to 1, and my result is proved. For some reason my pen didn't write. Let's try that again. That 4 was wrong. That 2 should have been in the denominator. Okay. And now what do I have? E to the sigma squared over 2 times 1 over root 2 pi sigma squared times the integral from minus infinity to infinity of e to the minus x minus sigma squared over 2 sigma squared dx. I set y equal to x minus sigma squared, so dy is equal to dx. This time you can read it in addition to hearing it, and I end up with e to the sigma squared over 2 times 1 over root 2 pi sigma squared times the integral from minus infinity to infinity of e to the minus y squared over 2 dy, and this whole business is just equal to 1 because the density function for the standard normal distribution is properly normalized, and presto, there's my answer. The second half of this problem is a little inequality that I need in order to do problem 4, and it's a nice exercise in proving obscure-looking inequalities. A general strategy is if you have an expression that has just a single minimum on the interval from 0 to infinity, it's always greater than or equal to its minimum value. So here I'm looking at a over the square root of t plus b times the square root of t. And if I graph that, it goes down, comes out like that. So it's got one minimum. Let's find it. I differentiate and get minus 1/2 a t to the minus 3/2 plus 1/2 b times t to the minus 1/2, and I set that equal to 0. Multiplying through by t to the 3/2 minus 1/2 a plus 1/2 bt is equal to 0, and that means the minimum is at t equals a over b. I plug that in, and a over root t plus b times the square root of t is equal to a divided by the square root of t plus b times the square root of t. The first term is equal to the square root of ab. The second term is also equal to the square root of ab. So the whole business has a minimum value of twice the square root of ab, and I have proved that a over root t plus b times root t is always greater than or equal to 2 times the square root of ab. I'm going to use that in the final problem. Okay, I think I can get this last problem on the same page, so you can see where I'm using the inequality I just proved. We're thinking about this random variable w sub t that's very important in the random walk theory of stock prices. That's normally distributed with mean 0 and variance t. And since w1 is normally distributed with variance 1, if I multiply it by the square root of t, I get another random variable that has the same distribution. What I want to show is that the probability of the quantity e to the minus sigma squared over 2 times t plus sigma times this w over t, that the probability that that is greater than or equal to n has a bound that is independent of t, and furthermore, that as m approaches infinity, this probability goes to 0. That's sufficient to satisfy the conditions for the Martingale convergence theorem, which will show that this converges to some random variable as t gets very large. So what do I have to figure out? This is just one of these exercises in changing things inside the parentheses. I want to figure out the probability that e to the minus sigma squared over 2 times t plus sigma times w sub t is greater than or equal to m. Let's take the log of both sides of the inequality, since in both cases we're dealing with numbers that are greater than or equal to 1, which means this probability is also equal to the probability that sigma squared over 2 times t plus sigma times w sub t is greater than or equal to log m. Now I want to isolate the w sub t, so I say, well, I'll just move the term involving sigma squared over 2 times t to the other side of the inequality. So that is greater than or equal to log m plus sigma squared over 2 times t. And to isolate w sub t still further, I say this is also the probability that w sub t is greater than log m divided by sigma plus sigma no longer squared over 2 times t. And now comes the clever step. Since w sub t has the same distribution as the square root of t times w1, this is also the probability that the square root of t times w1 is greater than or equal to log m over sigma plus sigma over 2 times t. And now I can get rid of that square root of t. This is the probability that w1, hey, that's something I know about because that standard normal is greater than or equal to log m over sigma times the square root of t plus sigma over 2 times the square root of t. But this is a function of t of the form a over the square root of t plus b times t, and we just proved that that is greater than or equal to so I will replace this by its minimum value. W1 is greater than or equal to the minimum value of this, which we just figured out is 2 times the square root of the thing over root t multiplied by the thing that multiplies the square root of t, or it's equal to the probability that W1 is greater than or equal to the square root of 2 log m. And as m gets bigger and bigger, the square root of 2 log m gets bigger and bigger, and the probability that the standard normal random variable W1 is bigger than that gets smaller and smaller. So as m approaches infinity, this probability approaches 0 independent of t. And that means that x sub t is not merely integrable, it's uniformly integrable, and therefore converges.